We're about to dive into a force that's completely invisible, but it's the hidden power behind our entire modern world. I mean, from the lights in this room to the phone in your hand, pretty much everything is driven by one single thing: electromagnetism. So, let's get into it. So, think about this for a second. What on earth could possibly connect these three things? You've got a simple little compass, a super complex piece of medical tech, and the basic wiring in your house. Well, the answer is a single unified force, and by the end of this, you're going to see exactly how they're all connected. Okay, here's how we're going to break it down. We'll kick things off with a totally accidental discovery. Then we'll get into the invisible rules of magnetism. After that, we'll see how electricity can create magnetism and how that can create real physical force. And finally, we'll see how all of this shows up in our world today. Right, so let's start at the beginning. Our story doesn't start with some carefully planned experiment, but with a moment of pure, dumb luck that completely changed how we see the universe. Picture this. It's 1820, and a scientist named Hans Christian Ørsted is in the middle of a lecture. He runs an electric current through a wire, and he just happens to notice that a compass sitting nearby suddenly twitches. Its needle just jumps. In that one single moment, the first real link between electricity and magnetism was proven. And that little observation, it laid the groundwork for, well, pretty much all modern communication. Radio, TV, you name it. And that discovery gave birth to this whole field of study. See, electromagnetism isn't about two different things. It's about one unified force. They are fundamentally linked. Electricity can create a magnetic field, which, of course, led to a really interesting question. Could it work the other way around? But before we get to that, let's really nail down the magnetism part of this whole thing. We need to understand the basic rules that make these invisible forces tick. This is rule number 1, the absolute bedrock of magnetism. And you've probably felt this yourself, right? You try to push two magnets together one way, and they push back, they repel. Flip one around, and they snap together. It's simple. Opposites attract, and likes repel. This is the fundamental principle that makes a compass point north. So, how does a magnet feel another one without touching it? It's all about its magnetic field. Think of it like a magnet's aura, or its zone of influence. If you bring another magnet or a piece of metal into that zone, it's going to feel a push or a pull. But how do you map something you can't even see? Well, it's actually pretty clever and surprisingly simple. You just take a tiny little compass, put it next to a bigger magnet, and make a dot where the North Pole is pointing. Then you just move the compass, line it up with the dot, and repeat. You're literally playing connect the dots to trace these invisible lines of force. And it turns out, these lines we trace, they follow some very strict rules. They always flow out of the North Pole and curve around into the South Pole. They're always in closed loops, and where you see the lines are all bunched up together, that's where the field is the strongest. Oh, and one more thing. They can never, ever cross. Okay, so now we get the rules of magnets. Let's circle back to Ørsted's discovery and see exactly how a simple electric current flowing through a wire can create its very own magnetic field. Now, there's a really cool little trick for figuring out which way that magnetic field is going. It's called the right-hand thumb rule. Seriously, just imagine grabbing the wire with your right hand. If you point your thumb in the same direction the current is flowing, the direction your fingers curl tells you exactly how the magnetic field is spinning around that wire. It's that simple. So what if we take that straight wire and we bend it into a loop? Well, now something really interesting happens. On the inside of that loop, all those magnetic field lines get bundled together, all pointing in the same direction. They basically team up, making the magnetic field way stronger right in the middle. And if one loop is good, well, why not use 100 or 1,000? That's what a solenoid is. It's just a coil with tons of loops of wire packed tightly together. When you run a current through it, all those individual magnetic fields add up to create one strong, super uniform field inside. It acts almost exactly like a regular bar magnet. This is how every electromagnet works. All right, now we get to the really good part. We know a current can create a magnetic field. But what happens when you take that wire with its current and you put it inside another magnetic field, say from a regular magnet? That's when things start to move. A scientist named André Marie Ampère thought about this.
He figured, hey, if the electric wire can push a compass needle around, then basic physics says the magnet has to be pushing back on the wire with an equal and opposite force. And he was right. This idea that a magnetic field can physically push on a wire with current in it is the secret to creating motion. So, which way is the wire going to move? For that, we've got another handy trick: Fleming's left-hand rule. Seriously, try this with your left hand. Point your first finger in the direction of the magnetic field, point your middle finger in the direction of the current, and your thumb will point exactly in the direction that the wire is going to be pushed. It's literally a blueprint for creating motion.
And this isn't just some abstract physics concept. This one single principle is what powers our world. It's how every electric motor spins. It's the basis for electric generators. It's how a loudspeaker cone vibrates to make sound, and how a microphone turns that sound back into electricity. This force is absolutely everywhere. Okay, let's bring all this theory right back down to Earth. We've gone from a twitchy compass needle all the way to the force that makes things move. Now let's look at a couple of places you can find this force at work, from cutting-edge medicine to the simple outlets in your wall. So get this. Your own body is electric. Your nerves work by sending tiny electrical signals, and those little currents create their own magnetic fields. Now, they are incredibly weak, about 1/1000th the strength of the Earth's magnetic field. But machines like MRIs are sensitive enough to pick up on these tiny magnetic whispers, and they use them to build these incredibly detailed maps of your body.
And what about the wiring in your house? Usually there are 3 wires. You've got the live wire, which brings the power in. You've got the neutral wire, which is the return path to complete the circuit. But maybe the most important wire for keeping you safe is the earth wire. Most of the time it does nothing, but if something goes wrong, it's like an emergency exit, giving any dangerous current a safe path straight to the ground instead of through you.
Now, things can definitely go wrong. Overloading is when you just try to pull too much current, like plugging way too many things into one socket. But a short circuit is even scarier. That's when the live and neutral wires actually touch, creating a super easy path for a massive, uncontrolled rush of electricity that can easily start a fire. So how do we stop that from happening? Well, the unsung hero of every circuit is the electric fuse. It's just brilliantly simple. It's a tiny piece of wire designed to melt at a really low temperature. If the current suddenly spikes to a dangerous level, that little wire instantly heats up, melts, and breaks the entire circuit, stopping the flow of electricity dead in its tracks.
So, there you have it. From a total accident in a Danish lecture hall to the force that spins our motors, lets us see inside our own bodies, and keeps our homes powered safely, electromagnetism is this invisible force that literally shapes our reality. Which leads to the final question: now that we understand it, what are we going to build with it next?